Example 2. The figure below of f prime of t shows the rate of change of f of t, the value of an investment over a 5-month period. We want to use this rate of change of value of the investment to answer the following questions. Part A. During which months is the investment gaining value? So we want to know when the original function is increasing. So using the idea of areas, we know that if the area is below the x-axis, that means that my investment is decreasing or losing money, which means that when I'm above the x-axis, I should be gaining area or gaining money in my investment. So I'm interested in where this is above the x-axis. So I'm going to be gaining money from month 3 to month 5 because that is where my area is positive. So I'm adding area and my total change is positive in my value. Now for part B, we want to know during which months is the investment losing value. So again, I'm interested in where I have negative area because that tells me where my original function is decreasing. So that happens from time equals 0 to time equals 3. And again, I know that because I can see that the area is below the x-axis. There's 2 more questions. Part C. During which month is the investment at a minimum? So when do I have the least amount of money? So I want you to think about the starting point of this investment. In month 0, my investment is decreasing, and it continues decreasing until month 3. At month 3, it starts to increase again. So we can use the information that we looked at in a previous section about critical points, and we can see that at month equals 3, our derivative changes from negative to positive. If we change from negative to positive, our investment was decreasing and then increasing, which makes that month a minimum. So in month 3, our value was at a minimum for this investment because we had lost all this money, but then in month 3, we turned around and we started gaining some. Part D wants to know, during this 5-month period, does the investment make or lose money? So it doesn't matter how much money you started with. What we want to know is what happened over this 5 months. And what you really need to recognize here is that more of the area is below the x-axis than above, which means that the amount that we declined or decreased was more than the amount that we increased, which means that overall we lost money. And again, we lost money because the area below is bigger than the area above, which means that we decreased more than we increased. So again, this is a way that we can use negative and positive areas to evaluate a situation. Let's look at another. Example 3. Consider the function f of x equals x cubed minus 7x squared plus 11x. Part A. Graph the function from 0 to 4. For which x values does this function cross through the x-axis? So let's see where we go from 0 to 4. So 0 is here, and 4, the function ends here. So we're going to ignore everything outside of that. From 0 to 4, all that stuff doesn't matter, which means that we cross through the x-axis right about here. So that happens visually at approximately 2.4. If we wanted to find this point more accurately, which we're going to need to, then we're going to have to figure out where our function equals 0. So let's take our function and do a little factoring here. So we have x cubed minus 7x squared plus 11x equals 0. I'm going to factor out an x term. So I'm left with an x squared minus 7x plus 11 equals 0. So either x equals 0 or this function in the parentheses equals 0. Since the point that I'm interested in is the one between 2 and 2.5, I know that I need to figure out when this parenthesis equals 0. Unfortunately, this is not something that is easily factorable. There's no two things that multiply to give me 11 that easily add up to give me -7. So instead, I'm going to have to use the quadratic formula. So I'm going to do the opposite of b plus or minus b squared, which is 49, minus 4 times a times c, which is 44, all divided by 2a, which is 2. So that gives me 7 plus or minus the square root of 5 divided by 2. So those two roots represent the point I want, and then this other point over near 5 that I'm not interested in because it's not in my interval. So taking the minus square root is going to give me the point I want. So 7 minus the square root of 5 divided by 2 is going to give me 2.3819 approximately. I rounded to 4 decimals. That was pretty darn close to my estimation at before, which was 2.4. I'm going to keep those 4 decimals, however, because it's a little more accurate. So let's see what else we want to do with this function. Part B. Consider the area that is above the x-axis. Set up an integral to represent the area above the x-axis and calculate the area using your calculator. Notice that the area above the x-axis happens first. So it starts at 0 and goes all the way until the point where we cross through, which we solve to be 2.3819. So if I'm going to set up an integral to represent the area above the x-axis, I'm going to set up an integral from 0 to 2.3819 of my function. So when I plug that all carefully into my calculator, I'm going to get 7.719. And it comes out as positive, which I was expecting. Part B, consider the area that is below the x-axis. Set up an integral to represent the area below the x-axis and calculate it on your calculator. So here, now my integral is going to go from where I crossed through, 2.3819, until 4, which is my second endpoint. So that's the area that's below the x-axis. When I plug this all into my calculator, it gives me a negative number, which is what I was expecting since it's below the x-axis. Negative 5.0531. So now I can evaluate a couple of other things. Part D. Use your answers from Part B and C to find the total area bounded by the function and the x-axis from 0 to 4. So here, the total area bounded means we need to look at the positive areas. So I'm going to take my positive area, 7.719, and then I'm going to add to it the area that's below. And I'm going to count it as positive because here I'm looking for total area. When I add those numbers together, I'm going to get 12.77 approximately. So the area bounded by the function and the x-axis has a total area of 12.77. Part E, if f of x has a derivative of little f of x, use your answer from Part B and C to find the total change of f of x from 0 to 4. So if we're looking for total change of the original function, and we know that the function that we have was the derivative, now we need to count anything above as positive and anything below as negative. We have two ways to do this. We can take our answers from Part B and C, which is what I have here, and I can add them together in the form that we got them from our calculator. So 7.719 plus negative 5.0531. And when I add those together, I'm going to get approximately 2.6659. I could have also taken my original function and integrated it from 0 to 4. So from 0 to 4, x cubed minus 7x squared plus 11x dx. Because my calculator will also count area above as positive and area below as negative. When I plug that in onto my calculator, I get 2.666 repeating, or 2.6667, which is pretty close to my approximation that I got adding up my areas. The difference is because I rounded in parts B and C, and so there's a little tiny bit of rounding error, but as you can see, it's minimal. So again, area above positive, area below negative, but only when you're talking about derivatives and the change of the original function. Let's look at another example. Example 3. Suppose a person is 50 miles away from their home and is driving in their car in a straight line. Their velocity is given in the graph below. So what I want you to notice is that the x-axis, or the t-axis here, is this line right here, which isn't super obvious, but it's implied based on this towards home, away from home situation. Now this is hour 1, hour 2, 3, 4, 5. So we're looking at what happens over a 5-hour period. Question A wants to know, when is this person farthest from their home? So I want you to remember that if we look at the area under a velocity curve, it's going to tell you your change in position. So from time 0 to time 2, the area under the curve is positive, which means that my distance away from home is increasing. And then from time 2 to time 5, the area under the curve is negative, which means I've turned around and now the area is negative, so the distance away from home is decreasing. So here I started 50 miles away from my home, and then my distance kept going. It kept increasing further and further away from my home until time equals 2. So notice that my derivative, or my velocity here, changes from positive to negative. That tells me that my original function was increasing and then decreasing. So that means that I'm going to have some sort of maximum, either local or global. So that means that it's going to be when I was the farthest from home, because the original function is position. So my position hits its maximum. That means that's the highest point, or the farthest away from home that I will be. So the when is time equals 2. Now, approximately how far away are they? Notice here that we don't actually have a function for this graph. We just have the picture. So we have to use the picture to try to approximate the area based on the numbers we have. So looking at this area between time equals 0 and time equals 2, it's almost like a triangle. So I think it'll be a pretty close approximation to treat this as a triangle. So doing so, I'm going to do 1/2 base times height. So using a triangle, I'm going to do 1/2 base times height. My base is 2 hours, and my height is 30 miles an hour. So the hours units are going to cancel, and I'm going to get 30 miles. So remember, I started 50 miles away. Now I went another 30 miles away. I'm driving away from my home, which means that at that time, at time equals 2, I am 80 miles away from my house. The 50 miles from before I started measuring, plus the 30 miles that I gained from time equals 0 to time equals 2. Part B wants to know, when is this person closest to their home? And approximately how far away are they? So in order to figure out when we're going to be closest to our home, we also need to understand how much area there is below the x-axis. Because at time equals 2, what's going to happen is the car is going to turn around and start driving back towards our home. So again, we can approximate this with a triangle. So here, again, I'm going to do 1/2 base times height. My base is now 3 hours because it's time 2 to time 5. And notice now that my rate, this goes all the way down to 60. So I'm going to put in -60. So that's going to give me -90 miles. And the negative means that I turned around and was driving back in the other direction. So that means that not only did I get to my house, I drove right past it, right? So I was 80 miles away, and if I turn around and drive 90 miles, then at some point I was actually at my house, and then I drove an additional 10 miles past it. So when this person was closest to their home, is going to be when the area is approximately 80. So we know that going all the way to 5 hours is a little too much. If we try to approximate how much area there is at 4 hours, we end up with some funky shapes, but we can certainly work with them. So if I'm approximating here, each one of these little blocks, right, is a 30 by 1. So each block is 30. So this one looks like half a block, so about 15. That's another 30. Now here, this area here looks like it's about 2/3 of a block, so another 20, I would approximate. So now I'm up to 65, and then I need to get to 80. So sometime between 4 and 5 hours, I should hit 80, because I know I'm about 65 at time equals 4, and therefore, between 65 and 90, I would have had to reach my home, or that negative 80 mark. So I'm going to say they're closest to home at time is approximately 4.5 hours. And at that point, they're at home. So again, I started with the triangle because that was my easiest approximation. But that wasn't good enough for my question. So I broke it down into the individual blocks to try to approximate the area of each little piece. And this little piece was 15. It was roughly half a block. This was a full block, so that was 30. This I said was 2/3 of a block, so that was 20. So it's not entirely correct. It's a pretty good approximation, and it's using the information I have. Part C wants to know approximately how far did they travel over the 5-hour period? Now, this question wants to know the total travel distance. It doesn't want to know where they ended up in relation to where they started. They want to know how many miles were driven. So we have to be a little bit careful here because remember, we drove 30 miles in one direction, and then we turned around and drove 90 miles in the other direction, which means that in total, we drove 120 miles. So if that's the question, I need to make sure that I'm counting that negative 90 miles as positive because I want to talk about the total miles traveled. So I have to take the absolute value in that case. If the question is how far are they from home at the end of the 5-hour period, then we would be 10 miles in the opposite direction than where we started because we would count that 90 as negative. But here, since we're talking about total travel, we want to count it as positive.